All right, last time in section 7.1, we talked about the definition of similarity. We know that similar polygons are ones that have angles that correspond equal, sides that correspond proportional. We know what that proportionality is. It means that if we rate if we write the ratios of the sides that correspond, all those ratios are equal to one another. Now, if you remember in our study of congruence, I presented you initially with a definition of congruence, and then we went on to triangle congruence shortcuts, that is, ways that we could prove triangles are congruent with less than complete information about their angle measures and side lengths. Well, we will do the same here with similarity. So we have a definition of similarity, so of course we could prove that two triangles are similar if we knew all of their side lengths and all of their angle measures. All we'd have to do is check for equality and proportionality. But we can conclude similarity with less than complete information about two triangles. And in this section, we will prove the first of our shortcuts to similarity, that is angle-angle similarity. And to do that, we will need a postulate, and I will give you that postulate in just a moment. And then we will go on to prove that if two angles of one triangle equal two angles of a second triangle, those triangles are similar to one another. Okay, so let's talk about the postulate to begin with. So let me ask you this first. Do you believe that we may take a polygon and scale it by the scale factor of our choice and thereby produce a second polygon similar to the first? The answer seems obvious to me. The answer seems yes, right? Like if you have a triangle, is it possible to create a second similar triangle with a scale factor of 3? That is, does there exist a second triangle whose angle measures are the same as the first, but whose side lengths are 3 times that of the first? And the answer seems to me quite obviously yes. So that then is our postulate. And here's the statement of it. So let us say that we're given a polygon that we'll call P and a positive quantity K. That will be the scale factor, of course. We may construct a second polygon Q such that P and Q are similar with the scale factor K. Okay, that is, for any given polygon and some scale factor K, there is a second polygon that is similar to it, where the scale factor from the first to the second is that K. Okay, so what will happen is this. We'll use this postulate together with what we know about triangle congruence to prove 3 similarity principles, let's call them. These are angle-angle similarity, what we'll prove today, and then SAS similarity and SSS similarity, which we will prove in the next section. So note again that these are shortcuts to similarity. That's what's really significant about them. They will allow us to prove that triangles are similar with only limited knowledge of side and angle measures. In this case, we will be able to conclude that triangles are similar if all we know is angle measures of triangles. Side lengths are not required. Okay, so here's the statement of angle-angle similarity, or of course AA similarity for short, or we could also simplify in a further way if we like. So let me note that as an addition. So we could also call this angle-angle and then simply write the similarity symbol after it. And what it says is this. If two angles of one triangle equal two angles of another, then those two triangles are similar. Now, just a quick note about this before we go to prove it. Um, what do we know when two angles of one triangle equal two angles of another? I mean, what did we know in a previous chapter in particular? The chapter where we proved the triangle angle sum theorem, chapter 4. We know that, of course, the third pair of angles are equal as well. So we could, of course, call this angle-angle similarity. Angle-angle equality implies angle-angle equality, but we shorten it and call it simply angle-angle similarity because, of course, we like short names and we can get away with them. Okay, so here's the setup of the proof. We have two triangles, ABC and RST. I know that angle A in the first is equal to angle R in the second, that angle B in the first is equal to angle S in the second. So we have two angles of one equal to two angles of the other, and we will prove that as a result of this, the triangles are similar. That is, the triangle ABC is similar to triangle RST. Now, here's the strategy, okay? We will construct a third triangle that I will call XYZ that is similar to ABC and congruent to RST. Perhaps I should write this out. So at the end of this proof, here's what we will know. I will know that triangle ABC is similar to triangle XYZ, and I will also know that triangle XYZ is congruent to triangle RST. Now, we've seen this situation before. This is something that I had you consider in the first section of the chapter. We know that if we have one triangle similar to a second, that second congruent to a third, then it follows from this that first and third are similar, as seems quite plausible, but I did have you prove this. And that's what we will use. Okay, so the whole point of this proof, or the whole strategy behind this proof, is to produce that third triangle XYZ that's similar to ABC and congruent to RST. So how will we create this this third triangle XYZ? Well, we need a scale factor, right? We'll use this triangle similarity, or just similarity postulate that I stated just a moment ago. And the postulate says that if we've got a scale factor and a polygon, we can produce a second polygon similar to the first by use of that scale factor. So we need a scale factor, and it can be any quantity we like. So I say let that quantity be the ratio of RS to AB. That is the side length of side RS divided by the side length of the length of side AB. Okay, let's use that. Now, of course, the question will arise, why make that the scale factor? Well, my answer is two-part. We can if we want. I mean, RS over AB is some quantity, of course. It's some positive quantity, obviously, because both RS and AB are positive quantities, so we could definitely use it. And then the second part of my response is it does the work that we need it to do. Okay, so this is our definition of the scale factor, and we will use the scale factor to construct the triangle XYZ. Okay, so what we do again is we take the triangle ABC and we scale it by the scale factor K, defined before, to produce a similar triangle XYZ. And this is just an application of our similarity postulate, right? We can always use a scale factor to produce a second similar polygon, okay? Well, what then do we know about the relationship between ABC and XYZ? Well, they're similar, obviously, by that similarity postulate. And that means that, among other conclusions, that angles that correspond are equal. So in particular, angle A is equal to angle X, and angle B is equal to angle Y, as shown in the diagram. And notice as well that I've also shown what the side length XY must equal. We scaled side lengths of ABC by K to get the side lengths of XYZ. So of course then XY is K times AB. AB and XY correspond. All right, so now let us consider the relationship of triangle XYZ to triangle RST. Well, we know just by definition that K is equal to RS over AB. That means, if we do just a little bit of algebraic work with that equation, that RS is K times AB. Simply multiply both sides by AB. Okay, so RS is K times AB. So there it is in the diagram. RS is K times AB. Also, XY was K times AB, as we noted before. But notice too that R was equal to angle A, which makes it equal to angle X. S was equal to angle B, which makes it equal to angle Y. And then we have what you see in front of us. I have these two triangles. I have two angles, that is XYZ and RST. I have two angles of one equal to two angles of the other, that is X and Y equal R and S, respectively. And then I have the included sides equal as well. And of course, then that it follows that these two triangles, XYZ and RST, are congruent. And they are congruent ultimately by ASA congruence. Okay, so this triangle that I created by use of my similarity postulate, that is triangle XYZ, is congruent to RST by ASA congruence. So here's where we are. I know that ABC, if I consider its relationship to XYZ, that's similarity. And then I know that the relationship of XYZ to RST is congruence. That is, I have one triangle similar to a second. That second is congruent to a third, so it follows by a result proven in section 7.1 that the first is similar to the third, which is precisely what we wanted to prove. Okay, so that is the result. Now, let me take just a moment to reflect upon what angle-angle similarity really tells us. Okay, what it tells us is this, is that triangles with equal angles are similar, but then of course by the definition of similarity, we know that their sides are proportional. Now, if we collapse this down, what this really says then is that in triangles, equality of angles implies proportionality of sides. I'll say that again, it is extremely important for us. Equality of angles in triangles implies proportionality of the sides. This is certainly one of the most important results of the class, and it is perhaps the single most important, the single most powerful result in the entire year. And we will seen it put to use repeatedly in this in the next chapter. And as a matter of fact, this is a teaser for work that we will do in the next chapter. This ultimately can be used to prove the Pythagorean theorem, okay? And it's a really quite ingenious proof. It's the standard proof of the Pythagorean theorem that you first see in a class like this, but it's really quite ingenious, and we will see that before too long. Actually, we will see the idea behind the proof of the Pythagorean theorem by the end of this chapter, and it will involve self-similarity, which is a really quite extraordinary idea. All right, I'll leave you with that. And the next time we will talk about SAS similarity and SSS similarity.